Proton NMR spectroscopy is probably one of the most powerful techniques in organic chemistry, but also one of the most frustrating. If you look at spectra and all you see are lines and it doesn't make any sense, this video is for you. We're going to go over the 4 things that you can pull out of a spectrum in order to understand and identify the unknown, and to also go from structure to spectra. So let's get started. Whenever we're looking at NMR, there's 3 things that we can identify. We can identify the number of H. This is coming from the integration. We can identify the chemical environment, which is coming from the ppm. And we can also determine the neighbors, also known as the spin system. And this is from the splitting. So let's analyze this spectrum and try to see if we can pull out these 3 pieces of information. I'm going to label my peaks A, B, C, and D. And I'm going to start to make a table where I have A, B, C, and D. I'm going to need the integration, the ppm, and the neighbors, or the splitting. I can also include a column for what that means for neighbors. So right now, this spectrum is not normalized. That means that there's just some random integration here that we have to normalize. Integration is going to be the area underneath the curve. So that's going to be coming from this number here. If I normalize this, I see that this is like 1, 1, 1. And then this would maybe be 1.5. And because I can have 1.5 H, I'm going to have to multiply everything by 2. So this would really be 2, 2, 2, and 3. We have a formula of C4H9, so let's see if that makes sense. 3, 4, 5, 6, 7, 8, 9. So that's good. This integration is telling me the number of H. So if I'm looking at peak A, it has an integration of 2. That means that I have a CH2. If I'm looking at the integration of B and C, they're also 2. So these would also be CH2. And if I'm looking at the integration of D, I see that that is 3. So that would be a CH3. And now I'm going to tabulate the ppm. Peak A is around 3.4. I take it from the middle of the peak, but I don't have to be that exact. Peak B is around, 1.8. Peak C around 1.5. And peak D around 1.0. Having this information listed and tabulated makes it really easy for me to go to a reference table for NMR and compare. Now, if I'm looking at the splitting, I see that there are 3 peaks. 3 peaks is going to be a triplet. Here I see that there are 1, 2, 3, 4, 5, which is going to be a pentet. Here I see 1, 2, 3, 4, 5, 6, which is going to be a sextet. And here I see 1, 2, 3, which is going to be another triplet. Whenever I'm thinking neighbors, I'm thinking n minus 1. And so that means if I'm a triplet, I actually have 2 neighbors because I'm going to have the splitting minus 1. So that tells me that A is going to be next to a CH2. B being a pentet is going to have 4 neighbors. C being a sextet is going to have 5. And D being a triplet is also going to have 2. And so with this information, this is everything that I need to figure out what this spectrum is. In order to put this together, I kind of like to make little fragments. So I'm going to have C that has HA. I'm going to have a C that has HB. I'm going to have a C that has HC. And I'm going to have a C that has HD. And then I'm going to have to put these together, right? If I'm looking at my formula, I have 4 carbons, 1, 2, 3, 4. So that's good. I don't have any carbons with no H's. And I have a bromine. So these are all the fragments that I'm trying to put together. There's a lot of things that I can do from here. I can go by the splitting. I can go by the chemical shift. I usually start with chemical shift and then I go to splitting after. So if I'm looking at the chemical shift, the only one that really stands out to me is this 3.4. These others are around 1 to 2, so these are giving alkyl. They're not really next to electron donating or withdrawing groups. They're just kind of like neutral alkyl. This 3.4 is telling me that I'm going to be near some electron withdrawing group. In this case, the only electron withdrawing group that I have is bromine. So to me, that's going to suggest that bromine is connected
to the carbon that has HA. So that's going to be those. I see that HA has two neighbors, and so that could either be these or these. And I'm not really sure yet. If I look at HB, I see that HB has four neighbors. So because it has four neighbors and I only have these CH2s and CH3, it has to be between two CH2s. So that's actually going to tell me that HB is in between HA and HC. HC has five neighbors, and so I only have one more carbon to connect to, but I can confirm because I see 1, 2, 3, 4, 5. So this would be my structure, where again, these are A, these are B, these are C, and these are D. Honestly, if you have this tabulation, you have everything. Even if your exam's like written and you have no idea what the structure is, but you write this tabulation, you get half credit because you've correctly analyzed the spectra. So this is something to practice. Here we went from an unknown to a formula, but we can also go from a formula to a spectrum. So let's look at this here. And let's make a table of what we think is going to happen. Whenever we're predicting spectra, we want to draw on all of the hydrogens so that we know what we're looking at. I see that there's hydrogens here. I also want to look for symmetry to see if any of the hydrogens have the same chemical environment. I see that these methyl ones are all going to be the same, so I'm going to call them A. Same with these, I'll call these B. But if I draw a line here, I see that I could fold this molecule in half and have the same thing. This H is identical to this H, and I can't tell them apart. That means that they're going to be chemically equivalent, and they're both going to show up together. They're going to show up as one thing. Same thing for these here. These are going to be these. And again, I go to make my table. I have my H. I'm going to have A, B, C, and D. I want to predict the integration, the ppm, the splitting, and the neighbors. So I see A, there are 3 hydrogens, so that'll have an integration of 3. B also has 3 hydrogens, so that'll have an integration of 3. There are 2 HC, and there are 2 HD. So I can already predict that in my spectrum. If we're thinking about the ppm, we want to go to a reference table. Whenever we have this is known as a toluene, a methyl that's kind of next to an aromatic ring. These are usually around 2 ppm. When we have an alkyl that's directly attached to oxygen, these are going to be around 4 ppm. The aromatic ring could shift that a little bit, but around maybe 3 to 4. And then when we have the aromatic ring, the aryl region is kind of like 7 to 8.5. So these are going to be around 7 to 8 ppm. That's what we would expect to see. If we look at the neighbors, I see 1 carbon away from A, there are no hydrogen. So I don't have any neighbors. That means that if we're thinking n plus 1 for splitting, I would go from 0 to 1. I would have a singlet. If I look at B, my neighbors in oxygen, again, there's no hydrogen. So I would be 0. It'd also be a singlet. If I look at HC, the only H that I see is D. And D also sees C. So I have 1 neighbor, so I would be a doublet. Same thing for HD. So this is what we imagine the spectrum would look like. We could even sketch this out. Down here we're going to have a ppm, so 10, 5, 0, 10, 5, 0. So we said that HA is going to be a singlet around 2 ppm. So I draw that here. We saw that this is worth 3H, so I integrated it. B is going to be another singlet around 4 ppm, also worth 3H. And then around 7 to 8 ppm, we're going to see C as a doublet and D as a doublet, both worth 2 each. So this is what I would imagine the spectra looks like. Which one is C and which one is D is a little bit ambiguous. I mean, you won't need to know that level of detail for most NMR applications. But we do know that this one is A, this one is B, and these are C and D. And so with NMR, it's really important to work in both directions to make sure that you can both analyze an unknown and predict the spectra, because it's really common to get questions in both directions. Okay, now we're going to look at determining the identity of an unknown when we have the formula, the IR, and the NMR. What I'm going to start with is the double bond equivalent, or degrees of unsaturation. The DBE is going to tell us how many rings or double bonds or triple bonds, this type of unsaturation that we have. And this formula is going to be the number of carbon plus 1 plus the number of nitrogen over 2 minus hydrogen over 2 minus X over 2 as being halogens. There's another formula for this, but this is the one that I prefer to use. So if I look at my chemical formula, I see that we have 10 carbon plus 1. We have 0 nitrogen, we have 12 hydrogen, and we have 0 halogen. This is going to simplify to be 11 minus 6, which is going to be 5. Whenever we have a high DBE like this is going to suggest that we have some type of aromatic ring or conjugated system. I'm going to go for aromatic ring because this has 4 double bond equivalents. I'm going to look for evidence of the ring in the IR and in the NMR. Looking in the IR doesn't look particularly remarkable, but I do see this peak here. I'm always going to look kind of around this 1700 wave number region because this is a carbonyl stretch. It's going to be really prominent. I'm not going to be able to miss it if I have carbonyl. Another peak that I always look for is the one over here. If I had some big broad peak around 3500 wave number, this would tell me that I have an OH. And if I have something that kind of looks like that around the same wave number, that's going to be like an NH. I don't see either of those, so that's telling me that I don't have O or NH. Some support of the aromatic ring can come from these here. These are known as overtones, and that happens when I have a conjugated system. So I probably have some aromatic ring, but then I'm going to need one more double bond equivalent because this only takes care of 4. Now I'm going to do my tabulation for the proton NMR. I see that I have HA, B, C, and D. So I'm going to make my table. Then I look for the integration, I look for the ppm, I look for the splitting, and then neighbors. Here the integration isn't really given to us, so we have to use the relative peaks. This looks like the shortest height, so I'm going to take that one and call it 1. This peak looks about double that, so I'm going to call it 2. This peak looks about triple that, so I'm going to call it 3. And this peak is much higher. Just based on where the chemical shift is, I would say that it's about 6 times as much. I'm going to tabulate my ppm. Again, I don't have to be super exact. For A, I see I'm about 8.0. Here I'm about 7.3, 3.5, and about 1.2. This 8.0, 7.3 is also suggestive of aromatic ring, whereas 3.5 is telling me I'm next to some electron withdrawing functional group, and this is telling me I'm in the alkyl region. If I look at the splitting, it's a little bit hard to see. This is kind of like a doublet, maybe a doublet of doublet. In the aromatic, it can be a little bit complicated. B is giving, I would just call it a multiplet. If I look at C, what I see is 1, 2, 3, 4, 5, 6, 7. There should be a heptet. And then if I look at D, that's a pretty clear doublet. So neighbors in the aromatic region looks kind of funky. DD suggests that I have 2 neighbors. Multiplet, I could have any. Heptet, I'm going to have 6. And with a doublet, I'm going to have 1. So now we can start kind of putting these things together. Again, I'm pretty confident that I have an aromatic ring, so I'm just going to go ahead and draw that. And since that I have 5 protons in the aromatic ring, so that's going to suggest that I'm monosubstituted. So then HA and HB would be the ring protons. I also have this carbon with HC, and I have this carbon with HD. We can't have more than 3H on a single carbon, so there's actually probably going to be 2 of these that are symmetrical. I'm going to draw it like this so that I can reflect the symmetry. So now I'm going to think about putting these things together. What I notice about C and D is that they're in a spin system together. They see each other. I see that C sees 6H, and these 6H also have to see C. And so the only thing that has 6H is HD, and this also has one neighbor, which must be HC. What this is going to tell me is that HC is right in the middle of these 2 symmetrical HD, and this is what would give me the splitting that I observe. Now I have to think about how to put these things together. So spectra tells me that I have 10 carbons. Right now I have 6, 7, 8, and 9 drawn. I know that I have a carbonyl, so I'm going to add carbonyl. That would be carbon number 10 and the oxygen. And I'm going to connect that to my isopropyl group. And so this would be my unknown. On the aromatic ring, because I see this 2, 3, this often happens where the 2 is the one next to the functional group and the 3 are everybody else. And so that's how we would go about finding an unknown.
So I hope with this video, NMR is starting to make a little bit more sense. We better understand the integration, what the ppm means for chemical environment, how to analyze the splitting, get the number of neighbors, and piece together an unknown. Any questions that you have, drop them below, or feel free to visit stepsystem.org for more help and more information.